Hi, fellow Chem 152 students. My name's Emily, and I did my project on something called radiometric dating in the Grand Canyon. My passion is hiking. I love seeing all that this beautiful world has to offer. And of course, Arizona has some of the best hiking in the world, including the Grand Canyon, our most famous spot. And I had never been, but I did have the opportunity to hike rim to rim this past October. And it was really hard and I undertrained, and it was the longest hike I've ever done. But here I am to tell the tale. And I learned through this project that you can tell the age of just the absolute gorgeous rocks in the Grand Canyon. You can tell through a process called radiometric dating. So I'm going to briefly explain how that works. Radiometric dating is a process where you compare the parent isotope to the daughter isotope and see, if you know the half-life, how many have occurred, and so how old is that rock. So in my example, uranium-234 decays to thorium-230, and the half-life is 80,000 years. So if using really simple numbers just to get the point across, if there was 75% of the daughter thorium compared to just 25% of this uranium parent, then that means that there's been about 2 half-life cycles. And so if the half-life is 80,000 years, then that rock would be 160,000 years old, which is a young rock, but that explains radiometric dating. And here's the nuclear equation for that process. We've got uranium, isotope 238, that's 92 atomic number on the periodic table. And through alpha decay, alpha emission, then it becomes thorium-234. It's a new element. It's 90 on the periodic table now. That's the atomic number. And so for one half-life of this to occur, just a reminder, it's 80,000 years. So that's how uranium becomes thorium. That's the equation for that. And I have a word problem for my adventure in the Grand Canyon. So I did a little research and I found out that sloths were what lived in Arizona a million years ago. So if a sloth was going through the same landmark, I think it was called the subway tunnel, a million years ago, and at that point there was 16.89 grams of uranium-238 in that sandstone, how much was left 1 million years to the day later when I passed by it thinking about how I was never going to make it out of the canyon. So to solve this problem, the first thing that you have to do is solve for the rate constant K. This is a rearranged half-life equation solving. I have the half-life, that's 80,000 years, and I have this 0.693. So plugging in the numbers, I solve the rate constant K. And so here it is, 8.66 times 10 to the negative 6 over years. And I plug it into that first law problem. So here's the negative rate constant times the million years. That was the time. I'm looking for the ending concentration when I walk by. And here was the starting concentration when the sloth walked by. Plugging it in, here's an intermediate step. Then I find that when I walked by that rock, then there was 0.00293 grams left of uranium in that sandstone. So that's that word problem. And then finally, I just want to share with you a few more pictures because it's one of the most gorgeous places on earth. And if you look at that, then I mean, you probably can't help but share my passion for hiking a little bit because it's just such a special place. And I'm so glad I got to see it. And now I know a little bit more about it. All right. Thank you for listening.